The third talk in this session is on robust Fourier and polynomial curve fitting by Venkat Guruswamy from CMU and David Zuckerman from UT Austin. David's going to give the talk.
Okay, thank you. Can you hear me? Yes, okay. So this talk is about the fundamental problem of curve fitting. Curve fitting is the problem where you're given a bunch of data points and you want to find the curve, say, low-degree polynomial that fits best. So this is a well-studied problem. It has applications in statistics where it's called, excuse me, where it's called regression or polynomial regression, computer vision where you want to find the edges of objects, Fourier analysis, etc. There's also a related problem of finding curve fitting for periodic functions. So a periodic function is like a function on the circle where you're just given the angle from 0 to 2 pi. And here, instead of fitting an algebraic polynomial, you want to fit what's called a trigonometric polynomial, which is just a linear combination of sine k theta and cosine k theta, where k ranges from 0 to d, and d is called the degree of this trigonometric polynomial. And it's basically just a Fourier series approximation. So this talk is concerned with outliers. So it's well studied if there are no outliers. But here, here's a set of points. I don't know if you could see it, but there's a curve that fits almost all these points. But there are 3 points that are outliers. And the question is how to handle these at a high level. So in practice, if I ask a colleague in AI, they'll tell me they use ransack. So what they do here is they sample a small number of points and fit a curve to the sample. So if there are no outliers in the sample, then the curve may be a fit for all the inliers. An inlier is something that's not an outlier, right? So maybe it fits all the inliers, not just the points in the sample. And then they take enough samples so that with high probability, one sample contains no outliers. So this has a couple of problems. The first problem is that it handles just about log d over d fraction of outliers. So either the degree d has to be quite small or else you just have a small fraction of outliers. And the second problem is that it doesn't handle significant error in the inliers. So even if your sample point is good, just fitting a curve to those points may be bad for other inliers. Another idea in practice is to minimize the L1 norm. So this is known to be more robust. It is more robust than minimizing L2, which is kind of the standard technique. And lasso is used for robust linear regression and more. The problem is that we just don't know theorems similar to the one that we prove for this. There are different models. Zhao talked about one model in the previous talk. And that's sort of L2 based. Our results are incomparable. We're looking at the Aurora-Cote model. So in this model, there's an unknown degree d polynomial p, and we're just studying its behavior on the interval -1, 1. And we'll assume by scaling that the range is also -1, 1. So the input, we've given a bunch of points in the interval across the interval. And the promise is that for most I, we'll explain what that means later, the yi is close to the polynomial evaluated at ai. So say it's in most delta. Think of delta as maybe a small constant or maybe 1 over poly log d. And so it's not a tiny value. And the hope is to output a degree d polynomial q, which is pretty close to p. We can't hope to output p exactly. You could always shift p up or down by delta. But we hope to get pretty close in the L infinity norm, where we measure the L infinity norm just as the maximum over the interval -1, 1. And of course, there's a natural analog of this problem for trigonometric polynomials. Aurora-Cote just studied algebraic polynomials, but this is natural analog. So even the outlier-free case is non-trivial. So let's start talking about that first. So here we assume that the AI are evenly spaced. And you ask, for what n is the answer unique up to order delta? So just information theoretically. So you have to worry about polynomials like this polynomial, 1 minus x squared to the d. Right? If x is bounded, if x is far from the origin, 1 minus x squared to the d is going to be tiny and very close to 0. So if you don't have any AIs close to the origin, then you won't be able to distinguish this polynomial from the 0 polynomial. And of course, if you're familiar with the Chebyshev polynomial, you know that has other extremal properties. So for algebraic polynomials, d squared points is necessary and sufficient. And the Chebyshev polynomial is extremal, and Aurora Cote give an algorithm which is basically using a linear program to find it. You can, for trigonometric polynomials, the situation is nicer. Order d points is necessary and sufficient. And the Chebyshev polynomial just corresponds to cosine d theta. Okay, and if the situation's a bit different, if we choose the AI, then order d points are necessary and sufficient for both settings. And the correspondence is just x equals cosine theta. So we can actually go back and forth between the two settings. So uniformly spaced points for theta corresponds to the so-called Chebyshev distribution, where there are more points close to -1 and close to +1. Okay, so that's the situation with no outliers. Now let's look at what happens when we add outliers. Well, the first thing is that we need the inliers, again, the non-outliers, the inliers to form some sort of cover. We can't leave an interval without any points because of the issue I mentioned earlier. So let's assume that the AI are roughly evenly spaced. So the Aurora Cote model says, okay, we start with all these AI. You pick a random subset of the AI to be outliers. And for any I chosen to be an outlier, the adversary can choose the yi value arbitrarily. And if it's chosen to be an inlier, then the yi has to be within delta of p of AI. But other than that, the adversary can choose it arbitrarily. So it's a very natural model. But it hasn't received a huge amount of study yet. So Aurora Cote did study this, and well, they showed a negative result. They said that if the outlier probability is bigger than half, well, of course, you can't hope to recover it uniquely, but you might have hoped to give sort of a list of polynomials, analogous to list decoding, that span all the possibilities. But they showed that actually there are exponentially many possibilities that are pairwise far in the L infinity norm. They also gave an exponential time algorithm for very structured outliers. So of course, it was an open question how to handle outliers. So we give the first polynomial time algorithm that handles a non-trivial fraction of outliers. You could do something actually with medians and stuff, but we can handle up to 1 over log d fraction of outliers at a high level. And we output a polynomial q that's pretty close to p. We hoped for order delta close. We can do order delta to the 0.99, or put in any constant less than 1 there. We also have some somewhat annoying restrictions, but it's not too bad. So delta, there's a lower bound on delta. So if we need delta to be at least 1 over poly log if we want to tolerate 1 over log fraction of outliers, or delta to be at least 1 over polynomial if we want to tolerate 1 over log squared fraction of outliers. And here, c is any constant, and b is a constant depending on c. So those are our results. And again, it's for both models, the algebraic or the trigonometric. And we also obtain a near optimal number of samples. So roughly ordered, so O tilde of d for the circle and O tilde of d squared for the interval. where the tilde hides polylogarithmic factors, like log cubed or log to the fourth. Okay, so I'll say I'll sketch our approach. Our starting point is the finite field setting where Venkat and I usually work more. So there's this Welch-Berlekamp algorithm for decoding Reed-Solomon codes. And so this is a great algorithm in the finite field setting. It recovers a polynomial from essentially the optimal fraction of errors. So the question is, can you adapt this to the real setting? So it's kind of obvious that the same method works in the real setting if delta is 0, but we want it to work for non-trivial delta. And we weren't the first to have this idea. Other people thought, oh, maybe something like this works. But they said, well, it doesn't actually seem to work if delta is bigger than 0. Kaltofen and Yang were able to make it work a little bit. They did something for small delta, but they were interested in relative error, and they didn't state any theorem, so it's a little hard to figure out exactly what they achieved, but they didn't achieve a theorem like what we achieved. So the point is that we are able to adapt the algorithm for much larger delta. So in order to sketch how we do that, let me first tell you about Welch-Berlekamp. So now we're in the finite field setting, F. So F is a finite field, although everything I say works for any field. So we have this unknown degree D polynomial. We have input. And we're promised that for most I, in the normal sense of most, P of AI actually equals Yi. So the main idea of their algorithm is to use this error locator polynomial. So what it does is it takes all the errors, so where Yi does not equal P of AI, and it just multiplies by x minus AI. So this is a polynomial of degree the number of errors. And why is that helpful? Well, let's set Q to be the error polynomial times the original polynomial. Well, now we have an equation that holds for all I. I claim for all I, Q of AI equals E of AI Yi. Why is that? Well, if AI is not an error, then we get then Q of AI is E of AI P of AI, and P of AI equals Yi. So these are equal. On the other hand, if AI corresponds to an error, well, then E of AI is 0. So Q of AI is 0, and this right side is also 0. So very simple. And then they just set up linear equations to find Q and E. And once you find Q and E, you can just divide to get P. So that's an overview of their algorithm, nice and clean. But again, it seems to rely heavily on really exactness. So what's our approach? Well, for one thing, we work in the trigonometric setting. We saw that we could go back and forth between algebraic and trigonometric, and we said that the trigonometric setting is cleaner, so we do that. So for the error locator, we don't start with a polynomial. We'll get a polynomial, or trigonometric polynomial, but we begin with a piecewise linear function f that looks like this. So this function is 1 when 1 for the inliers and 0 for the outliers. So it's just a piecewise linear function like this. We among ourselves, we refer to it as a mountain range function. And then we apply this classic theorem by Jackson, which I think should be better known in our community. So this is from 1930. When I mentioned Jackson to someone, they thought it was our Jackson, but this is an old one. So it's a function. So let's say we start with a function from the circle to the real numbers. Say it's continuous with Lipschitz constant lambda. So f of x minus f of y in absolute value is at most lambda times the absolute value of x minus y. So it's sort of like the derivative. Then there exists a degree m trigonometric polynomial g with L infinity norm at most order lambda over m. So for example, when this starts to be interesting in our setting when m is bigger than the Lipschitz constant lambda. So that's nice. We start with this piecewise linear function, and then we can get a nice polynomial. And so the first idea would be just, let's take our error locator polynomial to approximate the previous function f. If we do that, then the degree is too large. So that won't work. Instead, we have to modify f so that we only set it to 1 if the r closest neighbors to it are also inliers. The intuition being the slope was too much. We wanted to make the slope a bit narrower, so we only set it to 1 if a whole bunch of points nearby were also 1. Okay, so but actually that still doesn't work if we just apply it directly. Instead, what we ended up having to do is the following. We applied Jackson to get a coarse approximation, like say 0.1, some function f. And then we were able to set the error locator polynomial to just be f to a power. This turns out to be enough in our setting. And then, then we're in good shape. We use a linear program to, instead of just linear equations, now we have a linear program to find, we want to find that q and e. We'll call what we find q prime and e prime of the appropriate degree where q prime minus yi e prime is small. And q prime and e prime are close enough to the desired q and e. So the sketch of the final algorithm, we use this, as I just said, we find this q prime and e prime. And we can't just divide q prime by e prime like we did before, but instead we say that if e prime is above some threshold, then the true polynomial value is close to q prime over e prime. And in this way, we reduce to the outlier-free case. So now we just run the outlier-free algorithm on q prime and e prime for these values of I. Okay, so we give the first polynomial time algorithm in the Aurora-Cote model with outliers. So we handle a fraction like roughly 1 over log d of outliers, and our polynomial is pretty close to what we want. And we get the optimal number of samples up to log cubed or log to the 4th, depending on the exact setting. So this suggests some natural open questions, and Eric Price has basically solved these open questions. So he gave an essentially optimal algorithm using different techniques. So he's able to handle any fraction row of outliers. He's able to output. He doesn't have this annoying 0.99 in the exponent. He doesn't have any lower bound on delta, and he gives an optimal number of samples. Maybe there's a log d. Depending on exactly the model, there could be an extra log d factor that you could try to get rid of. So that's it. Are there other? But maybe our techniques are useful elsewhere. But you should read Eric's paper. Thank you. I see. So the question is, can this or related algorithms help solve problems in learning theory? And well, Venkat and I aren't really experts in learning theory, so we haven't really looked at that. But maybe, yeah, it sounds promising without really knowing anything. Right, okay, so the question is about the d versus d squared for algebraic versus trigonometric. So for trigonometric, you can have, I mean, for algebraic polynomials, you can have this Chebyshev polynomial, which, I mean, normally it's defined, normally it say it's at most 1 from -1 to 1, and then it jumps up to d just when you go up to 1 plus 1 over d squared. So you can shift it just a little bit to stay within the 1 minus 1 interval, and then you have just this 1 over d squared interval where it becomes very large. But if you, but the trigonometric polynomial just corresponds to cosine d theta in the trigonometric setting, and then that's a basis function that's you know, very nice. There's no, yeah. So somehow, right, if you choose the points, then you really want to choose more points close to -1 and close to 1 because that's where you could have these problems.